Once more, we slip back into the dark. Imagine standing at the center of a sphere 46 billion light-years in radius. Every photon reaching your eye has traveled through expanding space for nearly 14 billion years. Around you, a faint glow wraps the entire sky, the cooled remnant of the moment atoms first formed and the universe became transparent. And farther still lies a boundary not of sight but of consequence. The shell beyond which no signal you send will ever arrive. Tonight I want to show you that the universe has not one edge, but three, and that the most important boundary is not where seeing ends, but where reaching ends. If you'd like to leave a small light behind for others who wander these distances, a like or a subscription helps this channel reach them. Now let the screen dim, settle into the quiet. We're going to the edge tonight, to the place where the universe stops showing us its face. And you don't need to do anything but close your eyes and let the words carry you there. The cosmos will do the rest. We'll walk you to the horizon, and then we'll let you sleep among the galaxies that live just beyond it, unreachable and luminous, waiting in the dark. I am the cartographer of the dark. I have been mapping these distant places for longer than I can remember. Tonight we trace the three horizons together: what light allows us to know, what time allows us to reach, and what the universe keeps forever beyond our touch. The night sky feels infinite. Darkness spreads in every direction without limit, and the stars scattered across that darkness seem numberless, their light arriving from distances we cannot name. Yet every photon that reaches your eye is a messenger from a finite past. Looking outward and looking backward in time are not two different acts. They are the same act. The deeper you gaze into space, the further you travel into history. And that coupling between distance and time means the universe we observe is not a snapshot of now. It is a chronicle, layered in light, each shell of the cosmos frozen at a different moment in its long unfolding. The universe is old. 13.8 billion years have passed since the beginning, since the moment when space and time themselves emerged from conditions we can describe mathematically but not yet fully picture. That span of time is not abstract. It is the maximum age of any light that could have reached us. A photon emitted at the very beginning, traveling without pause across the expanding fabric of space, arrives today carrying an image of the universe as it was in its infancy. No light older than that beginning exists. No signal from before that moment can arrive, because there was no before in the sense we know. The observable universe is bounded not by walls in space but by walls in time. You might expect then that the edge of what we can see lies 13.8 billion light-years away. That would be the naive geometry. Light traveling for 13.8 billion years should cover 13.8 billion light-years. But the universe does not hold still while light crosses it. Space itself has been stretching the entire time those photons were in flight. The galaxies that emitted the oldest light we see today were much closer when that light began its journey. In the billions of years since, space has carried them away, and the light itself has been stretched, its wavelength pulled longer by the same expansion that pulled the galaxies apart. The edge of the observable universe, the horizon of what light has had time to show us, lies much farther than 13.8 billion light-years. It lies at a distance that reflects not just the age of the universe, but the cumulative stretching of space during all that time. This is the horizon we never noticed. It does not announce itself. There is no sign in the sky marking where the observable ends and the unobservable begins. The stars do not thin out. The galaxies do not fade into a wall. The darkness between them is the same darkness that fills the gaps nearby. Yet the horizon is there, invisible but absolute, a boundary written not in matter but in causality. Beyond it lie regions of the universe from which no light has had time to reach us. Not because those regions are empty or dark or fundamentally different, but simply because the universe is not old enough for their light to have crossed the distance. Every photon we see tonight, whether from a nearby star or a galaxy at the far edge of the observable sphere, is a traveler that began its journey within that causal boundary. Everything beyond it remains unseen, not because it is hidden by some veil, but because time itself has not yet permitted the meeting. The expansion of space complicates the picture in a way that feels almost paradoxical. A photon emitted from a distant galaxy does not simply coast through static space. It swims upstream against the stretching of that space, making progress toward us even as the galaxy that emitted it recedes in the opposite direction. For galaxies close enough, the photon wins. It arrives. For galaxies farther out, the photon still arrives, but only after eons of struggle, its wavelength stretched into the infrared. Then the microwave, its energy diluted by the expansion. The light from the most distant galaxies we observe today was emitted when those galaxies were much closer, and the space between us and them has grown by more than 1,000-fold since the light set out. The photon did not travel in a straight line through fixed space. It traveled through a space that was reshaping itself, second by second, across billions of years. This is why the edge of the observable universe is not a sphere 13.8 billion light-years in radius. It is a sphere far larger, shaped by the history of expansion, by the interplay of matter, radiation, and the geometry of space-time. The horizon we never noticed is a horizon of information, not of substance. It marks the boundary of what the universe has had time to tell us. Beyond it, the cosmos continues. Galaxies form, stars ignite, planets cool. None of that is invisible, because it is impossible to see. It is invisible because the message has not yet arrived. The photons that define this horizon are not all the same age. Some were emitted billions of years ago from galaxies that have since evolved, merged, or faded. Others were emitted more recently, from regions closer to us, regions that were themselves beyond the horizon in the early universe, but have since entered our observable sphere as time passed, and the horizon grew. The boundary is not fixed, it expands. Every moment that ticks by, new shells of the universe cross into visibility. Light that was too far away yesterday to have reached us arrives today. The horizon we never noticed is also a horizon that never stops moving. Yet even as the horizon of the observable grows, there is another horizon, quieter and less discussed, that is shrinking. The sphere of what we can observe is not the same as the sphere of what we can reach. Looking backward in time and sending a signal forward in time are governed by different geometries, and the accelerating expansion of space driven by dark energy has split those two spheres apart. The observable universe will continue to grow, but the reachable universe, the set of galaxies to which we could send a message today and have it arrive someday, no matter how far in the future, is smaller. Much smaller, and it is contracting. The night sky we see tonight contains galaxies that are already beyond our reach. Their light arrives, ancient and redshifted, carrying images of their youth. But any signal we send toward them today, even a beam of light traveling at the ultimate speed limit, will never catch them. Space is expanding too fast. The gap between us and them grows faster than light can cross it. They are visible, but untouchable. Observable, but unreachable. The horizon we never noticed has a twin, quieter and more final, and that twin is closing in. For now, though, the night sky remains full. 2 trillion galaxies populate the observable sphere, each one a system of hundreds of billions of stars, each one as real and as complex as our own. The light from those galaxies crosses the expanding void, arrives at our eyes, and becomes the image we call the universe. The horizon that bounds that image is not a failure of our instruments or a limit of our understanding. It is the shape of space-time itself, the edge of what light has had time to say. And as you drift towards sleep, the stars above you are not infinite. They are finite and ancient, and just barely close enough for their light to have found you. I wonder where you are tonight, listening in the dark. The stars look different from every place on Earth. Different constellations, different skies. If you'd like, leave your city and local time below. I'm curious who's out there, drifting through this with me. The particle horizon is not a wall you could touch, nor a surface marked in space. It is the maximum distance from which light, emitted at or after the beginning, could have reached us by now. It defines the radius of the observable universe, and that radius is not what you might expect. If the universe were static, frozen in place since its birth, the particle horizon would sit 13.8 billion light-years away, matching the age of the cosmos in years. But the universe has never been still. Space itself has been expanding the entire time photons have been traveling toward us, and that expansion stretches the distance between their origin and our eyes. By the time those ancient photons arrive, the places they left behind have receded far beyond the naive calculation. The particle horizon today lies not 13.8 billion light-years away, but 46.5 billion. The observable universe spans 93 billion light-years from edge to edge, a sphere centered on us not by privilege but by perspective. Every observer, anywhere in the cosmos, sees their own sphere of the same size, centered on themselves. The horizon is not a cage. It is the shape of what light has had time to show. This distance, 46.5 billion light-years, is often confused with another boundary altogether. The Hubble radius, the distance at which galaxies recede from us at the speed of light right now, sits much closer, only 14.5 billion light-years away. That boundary marks a different question entirely, one about motion, rather than visibility. The particle horizon is not concerned with how fast things are moving today. It asks only whether their light has had enough time to cross the growing fabric of space and reach us since the beginning. The particle horizon is not fixed, it grows. Every moment that passes, new shells of the universe enter our observable sphere. Light that was too far away to reach us yesterday crosses the threshold today. The horizon expands outward at the speed of light through space, but space itself is also expanding, and the interplay between these two motions determines what becomes visible and when. The boundary moves, but it moves slowly, patient as the cosmos itself. Imagine a photon emitted from a young galaxy in the early universe, a place that will one day become part of a distant supercluster we can barely resolve. That photon begins its journey through a universe much smaller and denser than today. It travels through expanding space, and as it does, the wavelength of the light stretches. The galaxy that emitted it recedes, carried by the growth of space, but the photon continues toward us, crossing void after void, threading the dark. Billions of years pass. The photon crosses regions that will later host clusters of galaxies, filaments of matter still gathering, void still hollowing out. It does not stop, it does not slow. The universe around it cools, thins, accelerates its expansion. Stars ignite and fade. Galaxies merge. The photon, redshifted now into longer wavelengths, continues. By the time it reaches us, the galaxy that sent it lies 46 billion light-years away, far beyond the Hubble radius, receding faster than light. Yet, we see it. The photon arrives, carrying an image of that galaxy as it was, not as it is. The light is ancient, the source is unreachable. But the message is here. The particle horizon is the boundary of all such messages. Beyond it lie regions of space, whose light has not yet had time to reach us, no matter when it was emitted. Those regions exist. They contain galaxies, stars, perhaps observers of their own, looking out at their own horizons. but their light is still in transit, or was emitted so far away that even traveling at the speed of light for the entire age of the universe, it has not yet crossed the distance. That distance is not empty. Space beyond the particle horizon is not void or dark in any absolute sense. It is filled with the same kinds of structures we see within our sphere. Galaxies arranged in filaments and walls, voids spanning hundreds of millions of light-years, clusters bound by gravity, stars burning through their fuel. The cosmological principle, the assumption that the universe is broadly the same in all directions and at all locations on large scales, suggests that what lies beyond our horizon is not fundamentally different from what we observe within it. We have no reason to expect a boundary in the structure of the cosmos itself, only in the reach of the light that has had time to show it to us. The particle horizon is a horizon of information. It separates what the universe has had time to tell us from what it has not. Every photon that crosses it brings news from farther away and longer ago. The most distant galaxies we have observed lie near the edge of this sphere, their light stretched into the infrared, their images faint and distorted by the expansion of space. They appear to us as they were more than 13 billion years ago, when the universe was young and stars were just beginning to gather into the first galactic structures. But we cannot see all the way to the particle horizon itself. There is a wall closer in, a wall not of distance, but of opacity. In the early universe, space was filled with a hot, dense plasma of protons, electrons, and photons. The photons scattered constantly off the free electrons, unable to travel freely. The universe was opaque, a glowing fog with no clear sightlines. Then, roughly 378,000 years after the beginning, the universe cooled enough for electrons to combine with protons, forming neutral hydrogen. The photons were released. They have been traveling freely ever since, and we see them now as the cosmic microwave background, a faint glow of microwave radiation arriving from every direction. The oldest light in the universe. That wall of last scattering sits just inside the particle horizon, a shell we cannot see past with light. Beyond it, in the first moments, the universe remains hidden. The particle horizon is not the edge of the universe. It is the edge of the observable universe, the limit of what light has had time to reveal. The universe itself may continue beyond it, perhaps infinitely. Measurements of the curvature of space, combining data from the cosmic microwave background and the large-scale distribution of galaxies, constrain the universe's shape to within 0.2% of flat. A flat universe can be infinite, extending without boundary in all directions, or it can be finite, looping back on itself in a shape too large for us to detect. Current observations cannot distinguish between these possibilities. The particle horizon marks the edge of what we can know, not the edge of what is. Within that sphere, the observable universe contains roughly 2 trillion galaxies, each one a system of hundreds of billions of stars, each one as real and as distant as the next. Some lie close enough that we see them as they were only millions of years ago. Others appear as they were more than 13 billion years in the past, their light carrying the image of galaxies still forming, still gathering mass, their stars young and blue and bright. The particle horizon grows, but it grows into a universe that is also expanding. The sphere of the observable does not swallow distant galaxies in the sense of bringing them closer. It reveals them as they were, frozen in the past, their light finally arriving after billions of years in transit. The galaxies themselves, in the present moment, lie far beyond where their light suggests, carried by the expansion of space into regions we will never visit, regions that may already lie beyond the reach of any signal we could send. The particle horizon is a boundary of time as much as space. To look outward is to look backward. The farther we see, the older the light, until we reach the wall of the cosmic microwave background and the universe becomes opaque. The horizon is not a destination. It is the edge of memory, the limit of how far back the universe can show us its own history. And it is always growing, always letting in a little more light from a little farther away, as the cosmos ages and the sphere of the observable slowly, steadily expands. You have crossed the threshold where distance becomes time, where the question is no longer how far but how long ago. The particle horizon marks the boundary of everything that light has had time to show us since the beginning. Yet even that vast sphere, stretching 46.5 billion light-years in every direction, does not reveal the earliest moments. There is a wall closer than the edge, a luminous shell that wraps around the entire observable universe, and it is made of light itself. The cosmic microwave background is not a place, it is a moment, frozen in transit. Every direction you look, if you could see in microwave wavelengths, you would see the same faint glow, the same temperature, the same ancient light. It surrounds you completely, a sphere with you at its center. Not because you are special, but because every observer in the universe sees the same thing from their own vantage. The light comes from a time when the universe was young enough to fit inside a single description, small enough that every point in space shared nearly the same conditions. 378,000 years after the beginning, the universe had expanded and cooled to a temperature of roughly 3,000 degrees. Hot, by any measure we know, but cool enough for a transformation. Before that moment, the universe was a plasma, a sea of free electrons and protons, dense and bright and utterly opaque. Photons could not travel. They scattered endlessly off the free electrons, trapped in a fog of light and matter, unable to move more than a short distance before colliding again. There was no transparency, no line of sight, no way for light to carry information across space. Then the temperature dropped below the threshold. Electrons and protons combined to form neutral hydrogen atoms, a process called recombination, though it was the first time atoms had ever formed. The fog cleared. Photons were released, suddenly free to travel without obstruction, and they have been traveling ever since. That release, that sudden transparency, is what we see as the cosmic microwave background. It is the oldest light in the universe, the first light that could move freely through space, and it has been journeying toward us for more than 13 billion years. The photons were released from everywhere at once. Every point in the early universe participated in recombination. Every region sent out its own light, and that light has been spreading outward ever since. The light we see today was emitted from a shell of space that, at the time, was relatively close to the matter that would one day become us. But the universe has been expanding the entire time those photons were in flight. The shell from which they originated, called the last scattering surface, now lies at a distance nearly as great as the particle horizon itself. The plasma wall sits just inside the edge of the observable universe, a boundary not of space but of visibility. The photons themselves have changed. When they were released, they were visible light, the warm glow of a universe at 3,000 degrees. But as space expanded, their wavelengths stretched with it. The universe has grown roughly 1,100 times larger in linear scale since recombination, and the light has been stretched by exactly that same factor. Wavelengths that were once visible are now microwave, invisible to the eye, detectable only with instruments tuned to the cold whisper of radiation that fills the sky. The temperature of that radiation today is 2.725 degrees above absolute zero, a nearly perfect blackbody glow, the cooled remnant of the fireball that once filled all of space. The cosmic microwave background is a snapshot, a single slice through cosmic history, the moment when the universe became transparent. It is the farthest wall of light we can see with electromagnetic radiation. Before recombination, there is no light to observe. The photons that existed earlier are still there, encoded in the cosmic microwave background itself, but they carry no information from before the fog cleared. The universe before that moment is invisible to us, not because it did not exist, but because light could not travel freely to carry its image forward. Every measurement of the cosmic microwave background is a measurement of that single moment, stretched and redshifted but otherwise unchanged. The tiny variations in temperature across the sky, differences of only a few parts per 100,000, are the imprints of density fluctuations in the early universe, the seeds that would grow into galaxies and clusters and the vast cosmic web. The light itself is uniform, the same temperature in every direction to extraordinary precision, a testament to how smooth the universe was at that early time. The last scattering surface is not a physical shell. No matter exists there now in any special arrangement. It is simply the set of all points in space from which light emitted at recombination is reaching us right now. A moment from now, the cosmic microwave background we see will have been emitted from a slightly different shell, a little farther out. As the expanding universe brings new regions into view, the wall of light moves outward through space as we move forward through time, always maintaining the same distance from us, always showing us the same moment in cosmic history. You cannot see past it. No telescope, no matter how sensitive, can peer through the cosmic microwave background to reveal what lies beyond in time. The universe before recombination is not dark, it is opaque. Light existed, but it was trapped, scattered, unable to travel. The cosmic microwave background is the edge of optical transparency, the farthest back we can see with photons. Beyond it, other messengers might carry information, neutrinos, gravitational waves, but light itself falls silent. The glow surrounds you, a shell of ancient photons arriving from every direction at once, each one a traveler from the same distant time. The cosmic microwave background is the farthest thing you can see, and it is also the most complete map of a single moment ever made. It is the universe at 378,000 years old, seen from 13.8 billion years later, stretched and cooled but otherwise intact. The wall of light is not a barrier, it is a horizon, the limit of what electromagnetism can show us, the boundary between the transparent universe we inhabit and the opaque plasma that came before. The light has been traveling for almost the entire age of the universe. It has crossed a space that expanded beneath it, stretching its wavelengths, diluting its energy, but never stopping its motion. The photons are still moving, still carrying the imprint of that early moment, still filling the sky with a faint, uniform glow. The cosmic microwave background is not fading. It is cooling, redshifting further as the universe expands, but it will never disappear. It is woven into the structure of space-time itself, a permanent record of the moment when light was set free. The plasma wall sits just inside the particle horizon, close enough to the edge that almost everything we can see in principle we can see in practice. There is only a thin shell of space, the earliest moments after the Big Bang, that lies within the particle horizon, but before recombination, a sliver of time that remains hidden. The cosmic microwave background is not the edge of the universe. It is the edge of a chapter, the boundary between the age of opacity and the age of light. The glow is there, always, surrounding you from every direction, a shell of light from the moment the universe opened its eyes. We have been tracing the shape of the cosmic horizon, that sphere of ancient light that surrounds us, and now we arrive at a peculiar truth. There is not one edge to the observable universe. There are three, and each one answers a different question about what time and physics allow us to know or reach. The first horizon is the boundary of everything we can see. It is called the particle horizon, and it marks the maximum distance from which light could have reached us since the beginning. We encountered this boundary in the previous rung. that sphere stretching 46.5 billion light-years in every direction, enclosing all the galaxies whose ancient photons have had time to cross the void and arrive here. This horizon answers the question, what has had time to send us a message? It is the edge of our causal past, the shell enclosing every event from which a signal could have traveled to us in the 13.8 billion years since the universe became transparent. And this horizon grows. Every moment that passes, new shells of space enter our observable sphere, their light finally completing journeys that began when the cosmos was young. But there is a second horizon, closer and stranger, that marks a different threshold entirely. It is called the Hubble sphere, and it sits at a distance of roughly 14.5 billion light-years. This is the surface where right now the expansion of space is carrying matter away from us at exactly the speed of light. Beyond this sphere, galaxies are receding faster than light itself. This sounds impossible. It is not. The speed limit set by relativity governs motion through space. But the Hubble sphere marks something else. The expansion of space itself. A galaxy beyond the Hubble sphere is not racing through the cosmos at superluminal velocity. It is sitting quietly in its own patch of space-time, while the fabric between us and it stretches faster than photons can cross it. The distinction matters. Relativity remains unbroken. The universe simply does not care about our intuitions. Here is the strange part. We can see galaxies beyond the Hubble sphere. We see them all the time. Their light reaches us not because they are close now, but because they were closer when they emitted that light, billions of years ago. A photon leaving a distant galaxy begins its journey toward us, swimming against the current of expanding space. For a long time, the expansion carries it backward, away from us, even as it struggles forward at the speed of light. But the Hubble sphere itself is not fixed. It expands over time, and eventually it overtakes the photon, sweeping past it and leaving it in a region where space expands slowly enough that forward progress becomes possible. The photon resumes its journey. Eons later, it arrives here, bearing an image of a galaxy that is now, today, receding faster than light and therefore unreachable. The Hubble sphere does not answer the question of what we can see. It answers the question of what is receding faster than light at this moment. It is a snapshot of velocity, not a boundary of visibility. Then there is the third horizon, the one that governs the future. It is called the cosmic event horizon, and it marks the boundary of everything we could ever reach, even if we wait forever. Right now, this horizon sits at a distance of roughly 16 billion light-years, a little farther out than the Hubble sphere. It answers the question, what can still receive a signal we send today? A light beam emitted from Earth right now, traveling outward at maximum speed, will eventually reach any galaxy within 16 billion light-years, no matter how fast that galaxy is currently receding. But a galaxy beyond 16 billion light-years is already receding so fast, and the expansion is accelerating so relentlessly, that our signal will never catch up. The photon will swim forward forever, and the gap will only grow. This is the horizon of the reachable universe, and it is not growing as fast as the particle horizon. In fact, under the influence of dark energy, the property of space that drives the accelerating expansion, the event horizon will grow only a little farther, reaching a maximum of roughly 17 billion light-years before it stabilizes. After that, it will sit there, a fixed shell in the expanding cosmos, while galaxies beyond it recede into permanent isolation. 3 horizons then. The particle horizon, marking what we can see, growing steadily as the universe ages. The Hubble sphere, marking where recession velocity equals the speed of light right now, a shifting surface that expands as the universe's expansion rate slows. And the event horizon, marking what we can still reach, growing more slowly than the others, and destined to freeze in place while the cosmos continues to stretch. Each horizon is real. Each is a structure of space-time, not a failure of our instruments or a gap in our knowledge. They are consequences of the finite speed of light, the finite age of the universe, and the accelerating expansion driven by dark energy. They do not contradict one another. They simply measure different things. Consider a galaxy 20 billion light-years away, far beyond the Hubble sphere. We can see it. Its light, emitted billions of years ago when it was closer, has reached us. We have measured its redshift, mapped its spiral arms, catalogued its stars. But we cannot signal it. If we sent a message today, a beam of light carrying information outward at maximum speed, that message would never arrive. The galaxy lies beyond the event horizon. It is visible but unreachable, a memory we can observe but never touch. Now consider a galaxy 10 billion light-years away, well within the event horizon. We can see it, and we can still, in principle, reach it. A signal sent today would eventually cross the gap, though it would take tens of billions of years to arrive, and by the time it did, the galaxy would have receded much farther. But the connection is not yet severed. The event horizon has not yet passed it by. The reachable universe is smaller than the visible universe. Of the roughly 2 trillion galaxies we can observe within the 46.5 billion light-year sphere, only a small fraction lie within the 16 billion light-year event horizon. By volume, the reachable sphere is only about 6% of the observable sphere. The rest, roughly 94% of the galaxies we see in our telescopes, are already beyond reach. We can study their light, measure their motion, watch their stars ignite and fade, but we can never send them a signal, never visit them, never alter their future in any way. They are visible ghosts, receding into a region of space-time from which no causal connection will ever return, and the reachable sphere is shrinking. Each year, as space expands and distant galaxies accelerate away, the event horizon passes over a few more of them. Roughly 3 galaxies per year slip beyond the boundary, crossing from the reachable into the permanently isolated. In tens of billions of years, only the galaxies of our local group, the small cluster gravitationally bound to the Milky Way and therefore immune to cosmological expansion, will remain within reach. Everything else will have crossed the horizon. The Andromeda Galaxy, the Triangulum Galaxy, and a few dozen smaller companions will be all that remains of the reachable universe. The rest will still be visible, their ancient light still arriving, but they will be as unreachable as the surface of the cosmic microwave background. The 3 horizons do not align. They are offset shells, each one marking a different threshold in the geometry of spacetime. The particle horizon, vast and growing, enclosing everything from which light has reached us. The Hubble sphere, smaller, marking where recession equals light speed today. The event horizon, smaller still, marking the boundary of what we can still touch. They are not walls. They are surfaces in space-time, consequences of the way light and space and time interact in an expanding universe governed by general relativity. To ask which one is the true edge of the universe is to misunderstand the question. They are all edges, each one answering a different aspect of what it means to be bounded by the speed of light and the age of the cosmos. The particle horizon is the edge of the visible. The Hubble sphere is the edge of recession velocity equaling light speed. The event horizon is the edge of the reachable. Together they form a nested set of boundaries, each one real, each one a feature of the universe we inhabit. There is no alarm in this, no urgency. The galaxies beyond the event horizon are not being destroyed. They continue to exist, to form stars, to evolve, to shine. They are simply receding into a region of spacetime that will never again intersect with ours. The light they emitted long ago still reaches us, and will continue to reach us for billions of years, red-shifted and dimmed but still carrying information. What changes is not their existence but their reachability. The future has a horizon, just as the past does, and we live inside both. The universe has 3 edges, and each one is the shape of a question. What can we see? What is receding faster than light? What can we reach? The answers are different, and the difference is written into the fabric of spacetime itself. We have spoken of the particle horizon, the surface where light has had time to reach us since the beginning. We have stood at the wall of the cosmic microwave background, the farthest curtain of transparency. We have named 3 horizons, each marking a different boundary in the architecture of time and causality. But none of these horizons is the edge of the universe itself. They are edges of information, of light, of reach. The universe beyond may continue without boundary. Measurements combining the cosmic microwave background and baryon acoustic oscillations constrain the universe's spatial curvature to within 0.2% of flat. Consistent with a universe that is either infinite or very much larger than what we can observe. The observable sphere, that region 46.5 billion light-years in radius, may be a tiny patch within something vastly greater, or it may be a representative sample of all there is. Current observations cannot distinguish between these possibilities. Flatness, in the language of cosmology, means that parallel lines remain parallel, that the geometry of space obeys the rules we learned in school. A flat universe can stretch forever in all directions, an endless expanse of galaxies and voids and filaments, continuing past every horizon we have named. But flatness does not guarantee infinity. The universe may be finite with a shape that loops back on itself, a three-dimensional surface with no boundary, like the surface of a sphere but extended into one more dimension. A traveler moving in a straight line through such a universe would eventually return to the starting point, having circled the entire cosmos without ever encountering an edge. Searches for evidence of this looping topology have looked for circles in the sky, matched patterns in the cosmic microwave background that would reveal we are seeing the same patch of the universe from 2 different directions. No such patterns have been found on scales up to the diameter of the observable horizon. Many exotic topologies remain observationally allowed. The topology question is far from settled. The universe may be infinite, or it may be finite with a shape that loops back on itself. We do not yet know. What we do know is that the observable universe, the sphere of light that surrounds us, is not the whole. Beyond the particle horizon lies matter and structure we cannot observe. Their light has not had time to reach us. By the cosmological principle, the assumption of large-scale homogeneity and isotropy well supported within the observable sphere, there is no reason to expect the universe beyond the horizon to be fundamentally different from what we see. More galaxies, more clusters, more voids stretching in filaments and walls, the same architecture repeated in regions we will never observe. Standard cosmology assumes the universe beyond our horizon is similar to what we see. Whether that assumption holds and what lies beyond remains outside the reach of any observation we can make. The particle horizon is not a wall in space, it is a wall in time. Light from those distant regions simply has not had enough time to cross the intervening void. As the universe ages, the particle horizon grows. Every moment that passes, new shells of the cosmos enter our observable sphere, their ancient light finally completing the journey that began billions of years ago. But there is another horizon, one we have named in passing, that behaves differently. The cosmic event horizon marks the boundary of the reachable universe, the maximum distance from which a light signal emitted now could ever reach us. That horizon, currently about 16 billion light-years in radius, is smaller than the particle horizon. It lies within the observable sphere. Galaxies we can see today, galaxies whose light has already reached us, may lie beyond the event horizon, beyond the boundary of what any signal we send today could ever reach. Roughly 94% of the galaxies now visible to us lie beyond what any signal we send today could ever reach. We see them because their ancient light was emitted long ago, when they were closer, before the accelerating expansion of space carried them beyond the threshold. Their light has traveled for billions of years to reach us, crossing a void that has been stretching the whole time. We see their past, we cannot touch their future. The distinction matters. Beyond the particle horizon lies what we have never seen. Beyond the event horizon lies what we can never reach. The two horizons are different slices in cosmic history, different answers to different questions. One grows with time. The other, under the influence of dark energy, will asymptotically stabilize, marking a permanent boundary between the reachable and the unreachable. If the universe is infinite, then beyond our observable sphere lie infinitely many other galaxies, infinitely many other clusters, infinitely many other observers, each with their own observable sphere centered on themselves. A galaxy 30 billion light-years away has an observable universe centered on it, that overlaps with ours, but also contains vast regions we will never see. Their horizon and ours are different circles drawn on the same infinite plane. If the universe loops back on itself, if it is finite with a non-trivial topology, then the regions beyond our horizon are not truly separate. They are parts of the same finite whole, connected by paths we cannot trace within the observable sphere. Either way, the horizon is not a cage. It is a consequence of the finite speed of light and the finite age of the universe. Light travels at 300,000 kilometers per second, and the universe has been expanding for 13.8 billion years. Those two facts together define the size of the sphere we inhabit. The horizon is not a defect of our instruments or a limit of human knowledge. It is a real structure of spacetime, arising from the laws of general relativity and the history of cosmic expansion. The observable universe, the sphere of ancient light that surrounds us, contains an estimated 2 trillion galaxies, each averaging hundreds of billions of stars. That is the census of what light has had time to show us. Beyond the particle horizon, if the universe is infinite, there are infinitely more. If the universe is finite, there are finitely more, but still more than we can see. We do not know which. We may never know. What we do know is that the universe we observe is not the universe entire. The edge of the observable universe is not the edge of existence. It is the edge of what light has had time to say. The cosmos beyond continues, in forms we can only assume are similar to what we see, governed by the same laws, shaped by the same forces, stretching outward in space and backward in time, until both dimensions lose their meaning in the hot dense state we call the beginning. The particle horizon grows. The event horizon stabilizes. The cosmic microwave background surrounds us from every direction, a shell of light from the moment the universe became transparent. And beyond all of it, the universe may be infinite, an endless expanse of galaxies and voids, or it may loop back on itself, a finite shape with no boundary. Both possibilities are consistent with what we observe. Both are allowed by the measurements we have made. The universe holds its full extent as a secret, written in regions of spacetime we cannot reach, encoded in light that has not yet had time to cross the void. We have already traced the boundary of what light has had time to show us, a sphere 46.5 billion light-years in radius, expanding with every passing moment as new shells of the ancient universe slip into view. We have seen the wall of the cosmic microwave background, that last surface of scattering plasma, the farthest veil of transparency. But there is a third horizon, quieter than the others, and unlike them, it is not growing outward into the dark. It is closing inward around us year by year, galaxy by galaxy, shrinking the sphere of what any signal we send today could ever reach. This is the cosmic event horizon, and it marks the boundary not of what we can see, but of what we can touch with light itself. The distinction matters. The particle horizon tells us how far light has traveled to reach us since the beginning. The event horizon tells us how far light emitted now could travel into the future, no matter how long we wait. And because the expansion of space is accelerating, driven by the property we call dark energy, these two boundaries do not align. The sphere of the observable grows slowly outward. The sphere of the reachable shrinks inward, leaving more and more of the visible universe permanently beyond our influence. Dark energy does not push galaxies away like wind against a sail. It is woven into the fabric of space itself, a property intrinsic to the vacuum, causing the metric of the cosmos to stretch at an accelerating rate. The farther a galaxy lies from us, the faster the space between us expands, and beyond a certain distance the expansion becomes so swift that no signal, no photon, no ripple of gravity we send today could ever close the gap. That distance, roughly 16 billion light-years from where we stand, is the event horizon. Galaxies within that sphere can still, in principle, be reached by light we emit now. Galaxies beyond it cannot, no matter how patient we are, no matter how long the universe endures. And most of what we see lies beyond it. Of the 2 trillion galaxies scattered across the observable universe, roughly 94% are already beyond the reach of any message we could send. They are visible to us because their light was emitted long ago. When they were closer, when the universe was smaller and the space between us had not yet stretched beyond the threshold, we see them as they were, luminous and real, their spiral arms turning, their stars igniting and fading, but they are no longer part of the cosmos we can touch. The light we see from them is an echo of a time when they were reachable. That time has passed. The event horizon itself is not a wall in space. It is a surface in space-time, a boundary defined by the interplay of expansion and the speed of light. A galaxy that sits just inside the horizon today might still receive a photon we send, but only if that photon departs soon. A galaxy just beyond the horizon is lost to us forever, not because it has been destroyed, not because it has moved in any conventional sense, but because the space between us is growing faster than light can cross it. The photon we send will travel outward, always at the speed of light through the space immediately around it, but the destination recedes faster still, and the gap never closes. This is not a failure of the photon, it is the geometry of an accelerating cosmos. Consider the galaxies we can name. The Andromeda Galaxy, our nearest large neighbor, lies well within the event horizon, bound to us by gravity, safe from the pull of expansion. The Triangulum Galaxy, third member of our local group, will remain reachable for as long as stars burn. But venture farther. The Sombrero Galaxy, that elegant disk seen edge-on, glowing in the constellation Virgo, lies roughly 30 million light-years away, still comfortably within the sphere of the reachable. The Whirlpool Galaxy, its spiral arms traced in blue star-forming regions, locked in gravitational embrace with a smaller companion, is reachable. The galaxies of the Virgo cluster, hundreds of them bound together in a web of gravity, most of them are reachable, though the cluster itself lies near the edge of our local supercluster, and some of its outlying members are beginning to slip away. But step beyond the local volume, the galaxies of the Coma cluster, hundreds of millions of light-years distant, a dense swarm of ellipticals and spirals bound together by dark matter, are beyond the event horizon. We see them clearly, their light crossing the void to reach our telescopes, but no signal we send will ever arrive. The galaxies of the Shapley supercluster, one of the largest concentrations of mass in the observable universe, lie far beyond reach. We map their positions, measure their redshifts, trace the filaments of dark matter that thread between them, but they are no longer part of the universe we can influence. They belong to the past we observe, not the future we can shape. The event horizon is not static. It is growing but slowly, and the galaxies themselves are receding faster. The result is a kind of cosmic attrition. Each year, the horizon expands outward by roughly 1 light-year, but in that same year, the accelerating expansion of space carries distant galaxies farther away, and the net effect is that approximately 3 galaxies per year slip permanently beyond the boundary of the reachable. 3 galaxies, each one a system of hundreds of billions of stars, each one a universe unto itself, crosses the threshold and passes into the unreachable dark. Not destroyed, not dimmed, but separated from us by a gulf that no amount of time can bridge. This has been happening for billions of years. It will continue for billions more. The sphere of the reachable, 16 billion light-years in radius, is only a small fraction of the observable universe. By volume, it represents roughly 6% of the sphere we can see. The rest, the vast majority of the cosmos we map and study and photograph, is already beyond the horizon. The galaxies we observe in the deep field images, those faint smudges of light that formed when the universe was young, lie tens of billions of light-years away, far beyond the reach of any signal. We see their infant light, the photons they emitted when they were newly formed, but those galaxies as they exist today, evolved and aged and perhaps transformed beyond recognition, are lost to us. And the sphere continues to shrink. In tens of billions of years, when the stars we see tonight have burned through their fuel and faded, when the sun has swelled into a red giant and cooled into a white dwarf, when the Milky Way and Andromeda have long since merged into a single elliptical galaxy, the event horizon will have contracted to enclose only the galaxies of our local group. Everything else will have slipped away. The Virgo cluster, the nearby galaxy clusters that now populate our maps, will have receded beyond the horizon, their light stretched into invisibility, their signals lost to the accelerating void. A civilization arising in that distant future, looking out from a galaxy in our local group, will see a universe nearly empty. The cosmic microwave background will still surround them, cooler and more redshifted, but the galaxies beyond their own small cluster will be gone from view, carried beyond the horizon by billions of years of expansion. They will inherit a lonelier sky than ours. But that future is not yet. For now, we still see 2 trillion galaxies, scattered across a sphere 93 billion light-years wide, their light reaching us from every epoch of cosmic history. We see galaxies forming in the first billion years after the Big Bang, their ultraviolet light stretched into the infrared by the expansion of space. We see galaxies in their prime, spiral arms bright with newborn stars, ellipticals glowing with the steady light of aged suns. We see galaxies colliding, merging, transforming under gravity's patient hand. Most of them are beyond our reach, but they are not beyond our sight. The event horizon does not erase the galaxies that cross it. It severs the thread of future communication, but it leaves the past intact. The light we receive from a galaxy beyond the horizon is real, carrying information encoded in its spectrum, its brightness, its polarization. That galaxy continues to exist, continues to evolve, continues to burn through its reserves of hydrogen and helium, but it does so in a region of spacetime that is no longer part of our causal future. We are observers of its history, not participants in its fate, and this is the nature of the shrinking sphere. It is not a countdown to darkness. The universe does not empty itself of light. The galaxies do not vanish. They slip beyond the horizon, one by one, year by year, receding into a region of spacetime that is still part of the cosmos, still governed by the same physical laws, still filled with stars and planets and perhaps life, but separated from us by the geometry of expansion. The boundary is not a wall but a threshold, and what lies beyond it is not nothing but simply elsewhere, a place that exists in the same universe, but not in the same causal structure. The sphere of the reachable will continue to shrink until only the local group remains. The galaxies within our gravitational embrace, bound together by forces stronger than the pull of expansion, will endure as neighbors. Andromeda, Triangulum, the dozens of dwarf galaxies that orbit the Milky Way, these will remain reachable, visible, knowable. The rest will have slipped away, not into non-existence but into a region of the universe that we can see but never touch, a visible past with no shared future. The event horizon shows us the shape of time in an accelerating cosmos. It reminds us that the universe is not a static stage but a dynamic geometry, stretching and evolving, and that the boundaries we encounter are edges not of space but of causality. The galaxies beyond the event horizon are not lost in the sense of being destroyed. They are lost in the sense of being unreachable, separated from us by a distance that grows faster than light can travel. And so the sphere shrinks, quietly, 3 galaxies per year, a slow attrition that will continue for eons, until the cosmos we can reach is reduced to the small cluster of galaxies bound to us by gravity. The rest will remain visible for a time, their light growing fainter and more redshifted, until eventually even that fades. But that darkness is not an ending. It is a horizon, the edge of what light has had time to cross in an expanding universe. And beyond it, the cosmos continues, vast and luminous, forever out of reach, but never truly gone. Beyond the sphere where recession velocity equals the speed of light, galaxies are already moving away from us faster than light itself. This is not a violation of physics. It is instead a reminder that the universe obeys rules more subtle than the ones we first learned. Special relativity forbids any object from moving through space faster than light. That law remains unbroken. What recedes beyond the Hubble sphere is not a galaxy racing through the void at superluminal speed. It is the fabric of space itself that expands, carrying the galaxy with it. The distinction is not semantic. It is the difference between motion within space and the stretching of space as a whole. Imagine 2 points marked on the surface of a balloon. As the balloon inflates, the points move apart, not because they slide across the rubber, but because the rubber itself grows. The points have no velocity of their own relative to the surface. They simply find themselves farther apart as time passes. In the same way, distant galaxies do not travel. They rest in their local patch of spacetime while the metric, the underlying geometry, expands between us and them. The speed limit set by Einstein governs motion through space. A photon crossing the void, a particle accelerated in a collider, a spacecraft drifting between stars. All these obey the same constraint. Nothing moves through the local fabric faster than light. But the expansion of space is not motion through the fabric. It is a change in the fabric scale, a transformation of distances encoded in the equations of general relativity. The Hubble flow, the name given to this universal recession, is not a wind. It is the lengthening of every ruler, the dilation of every interval, a process that operates outside the domain where the speed limit applies. Galaxies beyond the Hubble sphere, some 14.5 billion light-years away, recede faster than light. We can still see them. This seems paradoxical until we remember that the light we receive today was not emitted today. It was released billions of years ago, when those galaxies were closer, well within the Hubble sphere, and their photons set out toward us through a universe that was smaller and denser than the one we inhabit now. Those photons have been traveling ever since. While they crossed the void, the universe continued to expand. The source galaxy, carried by that expansion, moved farther and farther away. At some point in the photon's journey, the galaxy crossed the Hubble sphere and began receding faster than light. But the photons themselves were already in flight, already on their way. They did not turn back. They continued to propagate toward us, each one a messenger from a region of space-time that has since slipped beyond a certain kind of reach. The Hubble sphere itself is not static. It expands over time. As it grows, it eventually overtakes the photons that have been struggling against the current of expansion. Once the Hubble sphere passes them, the photons find themselves in a region where space is expanding more slowly relative to their forward progress. They begin to make headway. They close the remaining distance. They arrive. This is why we can observe galaxies that are receding faster than light. We see them not as they are now, but as they were long ago, when they occupied a different position in a smaller universe. Their light has been stretched by the expansion, redshifted toward longer wavelengths, but it reaches us nonetheless. The image we receive is ancient, a fossil of light preserved across billions of years of cosmic growth. The galaxies we see near the edge of the observable sphere are not where we see them. They have moved on. By now, they lie far beyond the Hubble sphere, receding at velocities many times the speed of light. The light we receive tonight left them when the universe was a fraction of its current size, when those galaxies were young and closer, and the space between us had not yet grown into the gulf that separates us now. There is no alarm in this. It is simply the way space-time behaves when it expands. The recession is smooth, lawful, predictable. It does not tear anything apart at the local scale. Galaxies within a gravitationally bound cluster do not fly away from one another. The Milky Way and Andromeda will still collide billions of years from now, their mutual gravity stronger than the gentle pull of expansion at such small distances. It is only across the vast reaches between galaxy clusters, across hundreds of millions and billions of light-years, that the expansion accumulates into velocities that exceed the speed of light. The photons do not know they are racing against expansion. They simply travel, as photons do, at the speed of light through their local patch of space-time. From their perspective, if such a thing could be imagined, they are always moving forward. The universe around them stretches, and the wavelength of their oscillation stretches with it, but they do not slow, they do not stop, they persist. And so we receive light from galaxies that are now unreachable, that lie beyond the boundary of what any signal we send today could ever touch. We see them because the past is still visible. The light they emitted long ago has had time to cross the intervening space, even as that space grew, and the source slipped away. The view we have tonight is an archive, a record of the universe as it was, not as it is. The fact that space can expand faster than light in no way contradicts relativity. Relativity is a local theory. It governs the behavior of objects and signals within a small region of space-time, a region small enough that curvature and expansion can be ignored. Within that local frame, the speed of light is absolute. Nothing overtakes a photon. But, on cosmological scales, where the curvature of space-time and the dynamics of expansion cannot be ignored, distances themselves are not fixed, they grow. And the rate at which they grow, summed across billions of light-years, can exceed the speed of light, without any object ever moving faster than light through its local space. This is the resolution. Motion through space and the expansion of space are distinct. One is forbidden to exceed light speed, the other is not. The galaxies beyond the Hubble sphere do not break the law. They rest in the current, and the current itself flows faster than light, and there is no contradiction. We stand inside a sphere roughly 14.5 billion light-years in radius, the Hubble sphere, where recession velocities are subluminal. Beyond it, the universe recedes faster than light. And yet we see far beyond it, because the observable universe is not bounded by the Hubble sphere. It is bounded by the particle horizon, some 46.5 billion light-years away, the maximum distance from which light could have reached us in the time since the beginning. The light from those farthest regions set out when the universe was young, when the sources were much closer. It has been traveling toward us ever since, riding the expansion, redshifted and stretched and dimmed, but never stopped. It arrives tonight, and tomorrow night, and every night, a continuous delivery of information from the deep past, from regions that have long since receded beyond the Hubble sphere and now lie in the superluminal zone. There is no wall at the Hubble sphere, no barrier, no edge that photons cannot cross. It is simply a surface in space where, at this moment, the recession velocity equals the speed of light. Closer in, galaxies recede more slowly. Farther out, more quickly. The Hubble sphere is a marker, not a membrane. Light passes through it in both directions, inward from ancient sources, outward from observers, each photon obeying the local speed limit while the distances around it grow. The universe expands, and the expansion does not violate relativity, and we can see beyond the Hubble sphere, because the light we see is old. These three facts fit together without contradiction. They describe a cosmos that is larger than the naive calculation would suggest, more visible than the Hubble sphere would imply, and entirely consistent with the laws that govern spacetime. Galaxies recede, space stretches, light travels. And we, inside our luminous sphere, receive the messages sent long ago from regions that have since slipped into the superluminal current, carried not by their own motion but by the quiet, inexorable expansion of the fabric itself. Beyond the edge of what we can observe lies more universe. The light from those regions has not had time to reach us in the nearly 14 billion years since the cosmos became transparent. But there is no reason to believe the galaxies and filaments and voids suddenly stop at the boundary of our sight. The observable sphere is not a container, it is simply the radius within which photons have completed their journey to us. Beyond that shell, space continues, matter continues, time continues. Standard cosmology assumes the universe beyond our horizon resembles what we see within it. More galaxies arranged in filaments and clusters, more voids stretching between them, more stars igniting and fading in the same slow rhythms. The cosmological principle, the idea that the universe is broadly the same everywhere, when averaged over large enough scales, holds well within the observable sphere. Measurements of the cosmic microwave background and the distribution of galaxies confirm that no direction is privileged, no region fundamentally different from another. Extending that assumption outward is reasonable, though it remains exactly that, an assumption. We cannot test it. The light that would confirm or deny it has not arrived. Some models of the early universe suggest our observable bubble is one of many, each governed by different physical constants, each shaped by different histories. These ideas emerge from certain versions of inflationary cosmology, frameworks in which the rapid expansion that seeded the cosmos we see also spawned countless other regions, separated from ours by horizons we can never cross. The mathematics is coherent, the logic internally consistent, but the models predict nothing we know how to measure. A universe beyond our reach by definition cannot send us a signal. Whether such regions exist, whether the constants of nature vary from bubble to bubble, whether the word universe should encompass only what we see or everything that might be, remains outside the domain of observation. We can imagine these possibilities, map their consequences, but we cannot confirm them. The distinction between what lies beyond the particle horizon and what lies beyond the event horizon matters here. The particle horizon marks the shell from which light emitted at any point since the beginning could have reached us by now. It is a boundary in our past. The event horizon, by contrast, is a boundary in our future. It marks the farthest distance from which a signal emitted today could ever reach us, no matter how long we wait. The two horizons are not the same surface. The particle horizon sits at a distance of roughly 46.5 billion light-years, encompassing everything whose ancient light has completed the crossing. The event horizon lies closer, at roughly 16 billion light-years, encompassing only those regions with which we can still, in principle, exchange information going forward. Beyond the particle horizon, there are galaxies whose light is still in transit, photons that will arrive tomorrow or a billion years from now, adding new shells to the observable sphere as time passes. Beyond the event horizon, there are galaxies whose light will never reach us, no matter how many eons we wait, because the expansion of space is accelerating, and those regions are receding faster than their signals can close the gap. Both boundaries are real features of space-time, consequences of the finite speed of light, and the history of cosmic expansion. But they answer different questions. One tells us what we have not yet seen. The other tells us what we can never influence. The universe beyond the particle horizon is not a void. It is not empty. It is not less real than the galaxies we catalogue in our sky. It is simply farther away in time. If we could wait long enough, some of that hidden universe would come into view, its light finally arriving after a journey longer than the current age of the cosmos. But we cannot wait forever. The event horizon ensures that, as space expands, and the acceleration driven by dark energy continues, the reachable sphere shrinks. Galaxies that are visible to us now, whose light we receive, and whose spectra we measure, are already beyond the boundary of what any signal we send today could ever reach. We see them because their photons were emitted long ago, when they were closer, but they are receding, and the gap is widening, and no message we craft will ever arrive. Standard cosmology assumes the universe beyond our horizon is similar to what we see: more galaxies, more structure, more time. Whether that assumption holds and what lies beyond remains outside the reach of any observation we can make. The particle horizon is not a wall we might one day breach. It is a temporal boundary, a limit written into the geometry of space-time itself. The light from beyond has not had time to cross the distance. That is not a failure of our instruments or a gap in our knowledge that better telescopes might close. It is a fact about the universe we inhabit. If the cosmos is infinite, as measurements of its spatial curvature suggest it might be, then the observable sphere is an infinitesimal fraction of the whole, a single bubble in an ocean without shores. If the cosmos is finite but larger than what we see, the observable sphere is still only a part, surrounded by regions that obey the same laws but remain forever separate from us by the accident of distance and time. Either way, the horizon is not an edge of existence, it is an edge of access. The galaxies beyond our particle horizon do not know we are here. They cannot. No signal we have ever sent has reached them, and if the event horizon has already enclosed us relative to them, no signal we send ever will. They continue in their own time, their stars forming and dying, their planets cooling or warming, their light spreading outward into space, some of it aimed in our direction but not yet arrived, some of it aimed away, lost to the voids between clusters. They are as real as the Virgo supercluster, as real as the Coma cluster, as real as the galaxies we see silhouetted against the cosmic microwave background. They are simply farther. We do not know if the universe beyond our horizon is a mirror of what we see or something stranger. We do not know if the laws of physics are the same there, if galaxies form in the same way, If time unfolds at the same rate, we assume they do, because the alternative requires mechanisms we have no evidence for and cannot test. But the assumption is not proof. It is a choice, a reasonable extrapolation from the universe we can measure, extended into the universe we cannot. The horizon is not a mystery in the sense of a puzzle waiting to be solved. It is a boundary condition, a feature of the cosmos that arises naturally from general relativity and the expansion history encoded in the cosmic microwave background. The universe beyond is not hidden by a veil we might lift. It is separated from us by time and distance in a way that no technology, no future observation, no waiting can overcome. The light has not arrived. The light will not arrive. That is the shape of the cosmos. What lies beyond the observable universe is, in the most fundamental sense, unknowable. Not unknowable because we lack the tools, but unknowable because the structure of space-time itself forbids the exchange of information across that boundary. The horizon is absolute. It is not a challenge, it is a fact. And beyond it, the universe continues, indifferent to our gaze, vast and perhaps infinite, filled with galaxies we will never name and stars we will never see, each one as real as the sun. The horizon is not a cage. It is a consequence of the finite speed of light and the finite age of the universe. Every observer in the cosmos, no matter where they sit, carries their own sphere of visibility centered on themselves. A galaxy 30 billion light-years away has an observable universe centered on it that overlaps with ours, yet also contains vast regions we will never see. The horizon is not a wall built to keep us out. It is the shape of what light has had time to say. The cosmic microwave background, the particle horizon, the event horizon, these are not defects or limits of human knowledge. They are real structures of space-time, arising from the laws of general relativity and the history of cosmic expansion. They are the architecture of the universe we were born into. The edge is not an ending. It is the edge of what has arrived. As the universe ages, the observable sphere grows. New shells of the cosmos enter our view. The particle horizon, that radius of 46.5 billion light-years, expands with every passing moment. Yet under accelerating expansion, the reachable sphere shrinks. The event horizon, that boundary of what we could ever influence, remains fixed at 16 billion light-years, and the galaxies beyond it slip further away. The universe we can see and the universe we can touch are not the same. One grows, the other withdraws. The universe we inhabit contains an estimated 2 trillion galaxies, each averaging hundreds of billions of stars. 2 trillion island universes, each one as real as our own, each one unreachable and therefore luminous. The Andromeda Galaxy, the Triangulum Galaxy, the Sombrero Galaxy. These are neighbors, bound to us by gravity, close enough that their light reaches us in millions of years rather than billions. But the galaxies beyond the local group, the ones scattered across the deep field, the ones whose light set out when the universe was young, they are already receding faster than light. We see them because their ancient light was emitted when they were closer, and that light has been propagating toward us ever since. But no signal we send today will ever reach them. They are visible, yet beyond influence. Roughly 94% of the galaxies now visible to us lie beyond what any signal we send today could ever reach. The reachable sphere is shrinking. Each year, approximately 3 more galaxies slip permanently beyond our influence. In tens of billions of years, only the galaxies of our local group will remain reachable. All others will have crossed the horizon, their light redshifted exponentially toward invisibility, their existence continuing but their connection to us severed by the expansion of space itself. This is not a tragedy. It is the shape of the cosmos we were born into. The horizon is not a failure of our instruments, or a gap in our knowledge. It is the boundary of what time and light allow. We know the numbers. 46.5 billion light-years to the particle horizon, 16 billion light-years to the event horizon, 14.5 billion light-years to the Hubble sphere, where recession velocity equals the speed of light right now, 2.725 Kelvin, the temperature of the cosmic microwave background, that nearly perfect black-body glow that surrounds us from every direction, redshifted from the 3000 Kelvin plasma that filled the universe when it was 378,000 years old. These numbers resolve into a single image. We are inside a sphere of ancient light, surrounded by the cosmic microwave background like a warm shell, looking out at 2 trillion island universes. The horizon is not frightening. It is the edge of what light has had time to show us. Beyond the particle horizon lies matter and structure we cannot observe, their light not yet having had time to reach us. Standard cosmology assumes the universe beyond our horizon is similar to what we see: more galaxies, more structure, more time. Whether that assumption holds and what lies beyond remains outside the reach of any observation we can make. The universe may be infinite, or it may be finite with a shape that loops back on itself. Measurements combining the cosmic microwave background and baryon acoustic oscillations constrain the universe's spatial curvature to within 0.2% of flat, consistent with a universe that is either infinite or very much larger than what we can observe. Current observations cannot distinguish between these possibilities. The horizon as mirror. It reflects not what the universe withholds but what we are. We are beings who look outward and see backward in time. We are observers who carry our own sphere of visibility wherever we go. We are creatures who can calculate the radius of the reachable and know that it shrinks, and still find rest in that knowledge. The edge is not a boundary of space. It is a boundary of time. It is the distance light has traveled in 13.8 billion years, stretched by the expansion of space into a sphere 46.5 billion light-years in radius. It is the shell of the last scattering surface, the moment when photons were released from the hot plasma and began their journey toward us. It is the event horizon, the boundary beyond which no new information can ever reach us, however long we wait. We are inside the sphere. We are surrounded by the glow of the cosmic microwave background, that faint whisper of the early universe, cooled to 2.725 Kelvin, still bathing us in the afterglow of recombination. We are looking out at 2 trillion galaxies, each one a collection of hundreds of billions of stars, each one as real as the Milky Way, each one unreachable and therefore luminous. The horizon is not an ending, it is the shape of the cosmos we were born into, it is the edge of what light has had time to say. And it is enough. The universe has drawn 3 circles around us, and only now are we learning which one is closing. For most of human history, the night sky appeared infinite. The stars seemed endless, the darkness between them a void without measure. But every photon that reaches your eye is a messenger from the finite past, and the sky you see is not a map of space alone, but a chronicle of time. Looking outward is inseparable from looking backward. The light from a distant galaxy left its source when the universe was younger, smaller, denser. The farther you look, the deeper into history you see, until at last you reach a boundary not of space but of transparency itself. The observable universe is not 13.8 billion light-years in radius, though that is the age of the cosmos in years. Space has been stretching the entire time those photons were in transit. A photon emitted near the beginning has been traveling toward us for nearly the whole history of time. Yet the galaxy that released it has been carried away by the expansion of space itself. That galaxy now lies not 14 billion light-years distant, but more than 46 billion. The edge of the observable universe, the particle horizon, is a sphere roughly 46.5 billion light-years in radius. Across its full diameter, the observable cosmos spans 93 billion light-years of space. This is the first circle, the boundary of what light has had time to show us. It is not a wall, it is not fixed. Every moment that passes, the particle horizon grows. New shells of the universe enter our view, regions whose ancient light is only now completing its journey across the dark. The horizon expands at the speed of light through time, pulling back the veil 1 year at a time. What lies beyond it is not nothing. It is simply unobservable, its light still in transit or not yet released. But we cannot see all the way to that horizon. The early universe was a furnace. For the first few 100,000 years, matter and radiation were locked together in a hot, opaque plasma. Photons could not travel freely. They scattered endlessly off free electrons, trapped in a luminous fog. Then, roughly 378,000 years after the beginning, the universe cooled enough for electrons to combine with protons and form neutral hydrogen. The plasma cleared, the photons were released, and they have been traveling freely ever since. Those photons are the cosmic microwave background, a nearly perfect glow that surrounds us from every direction. It is not a distant object. It is a surface in time, the moment when the universe became transparent, stretched across the entire sky. The temperature of that glow today is 2.725 Kelvin, a whisper of warmth just above absolute zero, the relic heat of creation redshifted by a factor of 1100. The wavelengths have been stretched by exactly the same ratio that the universe has expanded. What was once a searing 3000 degrees is now a faint microwave hum, invisible to the eye but written into every cubic centimeter of space. The cosmic microwave background is the farthest wall of light. It sits just inside the particle horizon, a luminous shell marking the edge of optical history. We can see the glow, but we cannot see what lay before it. The CMB is not a place. It is a time, and it is everywhere. Every point in space was once at the Big Bang, and every point in space has a last scattering surface surrounding it. This is the second circle, the boundary of what light can tell us about the beginning. But there is a third circle, and it is the one that matters most. The particle horizon answers the question of what we have seen. There is another horizon that answers the question of what we can reach, and it is much closer. It is called the cosmic event horizon, and its radius is only about 16 billion light-years. This is the boundary of the reachable universe. A signal emitted today from within that sphere could, in principle, eventually reach us. A signal emitted from beyond it cannot, no matter how long we wait. The reason is dark energy. The expansion of space is accelerating. Galaxies beyond a certain distance are receding so fast that the gap between us and them grows faster than light can cross it. A photon emitted today towards such a galaxy will never arrive. It will chase the receding target forever, making progress through space, but losing ground to the stretching of space itself. The event horizon marks the point where that futility begins. Beyond it, no communication is possible, no influence can propagate. The future is severed. And that horizon is closer than the Hubble sphere, the surface, where recession velocity equals the speed of light right now. The Hubble sphere lies at roughly 14.4 billion light-years. Galaxies beyond it are receding faster than light at this moment, yet we can still see them. Their ancient light was emitted when they were closer, and that light has been traveling toward us ever since. The Hubble sphere itself expands over time, eventually overtaking those photons and allowing them to reach us. This does not violate relativity. The speed limit governs motion through space. Cosmological expansion is a property of space-time geometry itself. The fabric of space expands, carrying galaxies apart, and there is no limit to how fast that expansion can proceed. But the event horizon is different. It is not about what we can see, it is about what we can touch. Of the roughly 2 trillion galaxies in the observable universe, only about 6% lie within the event horizon. The rest, Some 94% of the galaxies now visible to us lie beyond what any signal we send today could ever reach. They are observable, but unreachable. We can see their light, study their spectra, measure their distances, but we cannot send them a message. We cannot visit them. We cannot know what they will become. They are slipping away. And the event horizon is shrinking. Not in absolute terms. It will grow slightly over the coming billions of years, approaching a maximum radius of roughly 17 billion light-years before stabilizing. But galaxies are receding faster than the horizon is growing. Each year, roughly 3 more galaxies cross the threshold and pass permanently beyond our influence. They do not vanish. They do not wink out. They simply drift across an invisible line in space-time, and from that moment forward, no information we send can ever reach them. They continue to exist, but they are no longer part of our causal future. This is the third circle, the boundary of what we can ever affect, and it is closing. In tens of billions of years, only the galaxies of our local group will remain reachable. These are the galaxies bound to us by gravity, close enough that the mutual pull overcomes the expansion of space. The Milky Way, Andromeda, Triangulum, and a few dozen smaller companions. The rest of the cosmos will have receded beyond the horizon. Their light will still be visible for a time, red-shifted toward invisibility, stretched into wavelengths so long that no instrument could detect them. And then, as the last photons cross the horizon, they too will fade. The universe beyond will still be there, vast and full, but it will be forever beyond reach and eventually beyond sight. This is not a defect. It is not a limitation of human knowledge or a failure of our instruments. It is a real structure of spacetime, arising from the laws of general relativity and the history of cosmic expansion. The particle horizon, the cosmic microwave background, the event horizon. These are not abstractions. They are the shape of the cosmos we were born into. The universe may be infinite. Measurements combining the cosmic microwave background and baryon acoustic oscillations constrain its spatial curvature to within 0.2% of flat, consistent with a universe that is either infinite or very much larger than what we can observe. Or it may be finite, looping back on itself in a topology we cannot yet detect. Current observations cannot distinguish between these possibilities. Beyond the particle horizon lies matter and structure we cannot see, and by the cosmological principle, there is no reason to expect it to be fundamentally different from what we observe here. Standard cosmology assumes the universe beyond our horizon is similar to what we see, but whether that assumption holds remains outside the reach of any observation we can make. Every observer in the universe has their own observable sphere. A galaxy 30 billion light-years away has an observable universe that overlaps with ours, but also contains vast regions we will never see. The horizon is not a cage. It is a consequence of the finite speed of light and the finite age of the universe. It is the edge of what light has had time to say. And now we know that one of those edges is moving inward. The verdict is this: the universe we can see is not the universe we can reach, and the universe we can reach is shrinking. 94% of the galaxies now visible to us lie beyond what any signal we send today could ever touch. They are luminous and real and forever beyond influence. The sphere of the reachable is contracting, not because space is collapsing, but because it is accelerating away. The future is smaller than the past. But the particle horizon is still growing. Every year, new light arrives from regions we have never seen. The observable universe expands even as the reachable universe contracts. We live in the brief era when both are true, when the cosmos is still revealing itself and has not yet fully withdrawn. We are inside a sphere of ancient light, surrounded by the cosmic microwave background like a warm shell, looking out at 2 trillion island universes, each one as real as our own, most of them already unreachable, and therefore luminous, untouched, and utterly themselves. The edge is not an ending, it is the shape of time made visible. We have traveled to the edge of what time and light permit. The particle horizon, 46 billion light-years out, marks how far photons have wandered since the beginning. The event horizon, 16 billion light-years away, draws the boundary of what any signal we send could ever reach. 3 horizons, 3 questions, 3 kinds of distance woven into the geometry of space-time itself. Beyond them, the universe continues. More galaxies, more structure unfolding in directions we will never see. The edge is not a wall, it is the shape of what a finite age allows us to know. If you are still awake, thank you for traveling this far. If you have already drifted, then the cosmos has done what it came to do. Wherever you are tonight, the dark will still be here. So will I. Come back tomorrow if you'd like. There are other edges to map. Rest well.